Hello and welcome to XP Actuarial's introductory video series. Today we will give a math refresher, part 2, and we will cover basic linear algebra concepts covered on the exam. The first thing we'll cover are the dimensions of a matrix. So say we have an n by m matrix, where n is the number of rows and m is the number of columns. So for example here we have one row and two columns, so this would be a 1 by 2 matrix. Here we have two rows and two columns, so this is a 2 by 2 matrix. And here we have two rows and one column, so this is a 2 by 1 matrix. Commonly on the exam, you'll either hear n by n or n by m. Now n by n means that the number of rows and number of columns are the same in the matrix, and n by m means that the number of rows differs from the number of columns. Now the second concept that's often tested is matrix multiplication. Now say we have a 1 by 2 matrix here, and we want to multiply it by a 2 by 2 matrix. Now to do matrix multiplication, this number and this number must be the same. Now to figure out the size of our new matrix, we simply cancel these two terms, and we're left with a 1 by 2 matrix. So the multiplication of a 1 by 2 and a 2 by 2 will give us a 1 by 2 matrix. Now the first term of the matrix, what we'll do is we'll take this row multiplied by this column. So a times a plus c times c. So we get a squared plus c squared as our first term. For the second term of the matrix, we'll take this row multiplied by this column. So a times b plus c times d. So AB plus CD. And we can look at a numerical example of this. Let's suppose we have a 1 by 2 matrix of 1, 2, and a 2 by 2 matrix of 1, 2, 3, 4. So again, we cancel these terms, and we're going to get a 1 by 2 matrix. So we take the first term of that matrix would be 1 times 1 plus 2 times 3, which is 7. And our second term would be 1 times 2 plus 2 times 4, which is 10. So we get the matrix 7, 10, which is a 1 by 2 matrix. Now the second concept used on the exam are determinants. And the most likely matrix sizes to be tested would be a 2 by 2 or a 3 by 3. Now with a 2 by 2 matrix, to find the determinant, you simply go A times D minus B times C. So AD minus BC. Now to get the determinant of a 3 by 3 matrix, we have to do one step further. And what we do is we break the matrix into three smaller calculations. So we take positive A times the determinant of here, minus B times the determinant of DG and FI, plus C times the determinant of this matrix here. So if we write this out, we need the determinant of this matrix, which would be EI minus FH. So it's EI minus FH, minus B times DI minus FG, plus C times DH minus EG. So that gives us the determinant of a 3 by 3 matrix. The next thing that we need to know for the exam is the length of a vector, or the norm of a vector. So suppose we have the vector ABC, and we want the length of that vector. We simply take the square root of the sum of the squares. So for example, say we have the vector 1, 2, 3. Now the length of that vector is simply the square root of 1 squared plus 2 squared plus 3 squared. Now that gives us around 3.741657. Now this length of a vector comes in handy when computing a unit eigenvector. So moving on, we'll then cover eigenvalues and eigenvectors. So suppose we have a matrix sigma. Now this sigma is an m by m matrix, and generally on the exam it will be a covariance matrix or a correlation matrix. And we want to find another matrix, an m by 1 matrix, which we'll label Vi, which contains which is the eigenvector I of matrix sigma, which is non-zero, and an eigenvalue lambda I, which is the ith eigenvalue of sigma. Now we need sigma times vi to be equal to vi lambda I. Now each vi has its own eigenvalue, lambda I. Now we also define capital lambda as a matrix of eigenvalues with the eigenvalues down the diagonal and zeros elsewhere. So it looks like this, lambda 1 to lambda n, and then we have zeros everywhere else. Now we also define a matrix V, which is an m by m matrix, and what it will contain is our eigenvectors in each column. So V1 would be here, V2 here, and so on. Now we also require that VV transpose is equal to I, which is the identity matrix, which has ones down the diagonal and zeros elsewhere. Now, to actually find the eigenvalues, we have to solve this equation. So we take the determinant of sigma minus lambda I. So lambda I is simply equal to lambda down the middle, diagonal, and zeros elsewhere. Now we set the determinant equal to 0, and then we solve for these lambdas. Now once we have the lambdas, which are eigenvalues, we then need to find the eigenvectors, and we do this by solving this equation. We take sigma minus lambda I, which is the ith eigenvalue, multiplied by I, all multiplied by vi, our ith eigenvector. We set this to 0, and we solve for the terms in this vi vector. So the easiest way to go over this is with an example. So suppose we have the covariance matrix below. To find the eigenvalues, we have to take the determinant of sigma minus lambda I and set that equal to 0. So we can, we'll note that lambda I, again in a 2 by 2 matrix, is simply lambda 0, 0, lambda. So we're going to take this matrix minus this matrix. So we get, and we want the determinant of that. So we get 0.16 minus lambda, 0.084 minus 0, which I'll omit, again 0.084 minus 0, and 0.09 minus lambda. And we want the determinant of that to equal 0. So now we simply solve the determinant, 0.16 minus lambda multiplied by 0.09 minus lambda minus 0.084 squared. Now we can rearrange this to get lambda squared minus 0.25 lambda plus 0.007344. And we set that equal to 0. Now we'll use the quadratic equation, negative b plus or minus b squared minus 4ac, square root of that, all over 2a. Now we can solve for our lambdas, which is 0.216 and 0.034. Now with these lambdas, we'll next solve the eigenvectors. So we'll solve the first eigenvector. And how we solve those is we take sigma minus lambda 1 I times v1, and we equate that to 0. So we know that lambda 1 is equal to 0.216, so we can substitute it into this equation. So 0.16 minus 0.216 is negative 0.056. 0.084 is still just 0.084, and the same over here. And then 0.09 minus 0.216 is negative 0.126. Now we multiply this by our vector v1, which consists of v11 and v12, and we set that equal to 0. Now we multiply these two terms with these, and we get our first equation, 0.056 v11 plus 0.084 v21 equals 0. And we can solve this equation, and what we get is that v11 equals 1.5 v21. So we bring this over here, divide by negative 0.056, and we get this equation. So now we can choose a value for v21. Let's suppose that value is 1. That would mean that v11 is 1.5. Now what's commonly done is to express the eigenvector as a unit eigenvector. So what we need to do is divide each term in this vector by the length of this vector. So the length of v1. Now the length of v1 would be the square root of 1.5 squared plus 1 squared. So that's the square root of 3.25. So we take 1.5 divided by the square root of 3.25 and 1 divided by the square root of 3.25, and that gives us our unit eigenvector. Now this would be 0.8320503 and 0.5547002. So now we have our two eigenvalues and our first eigenvector. So the next step is then just to solve for our second eigenvector. And here we use the equation sigma minus lambda 2I v2 equals 0. So now our second lambda is 0.034. So we'll put 0.034 into this, and what we get is 0.016 minus 0.034 is 0.126. And over here we again get 0.084, 0.084, and then we take 0.09 minus 0.034 is 0.056, multiplied by v12 and v22 equals 0. And now we get, again, a system of equations, but they're actually going to work out to be equal, so we only need to really use one of them. We set that equal to 0. And what we get here is that v22 equals negative 1.5 v12. So we bring this value over here, and we get negative 0.126 v12 divided by 0.084, and that gives us this equation here. So our v2 is simply, we can set v12 equal to 1, and that means that our v22 is negative 1.5. Now we need the length of v2, so the length of v2 is the square root of 1 squared plus negative 1.5 squared, and that gives us the same thing as before of 3.25 square root. So now we take these terms and divide by this value, and we get v2 to be equal to 1 divided by square root of 3.25, again, is 0.5547002, and negative 1.5 divided by the square root of 3.25 is negative 0.8320503. So we've solved for our two eigenvectors, v1 and v2, and we've also solved our two eigenvalues. Now that concludes the lesson on linear algebra. I hope this will help you with your exam, and choose XP Actuarial, as we're here to help you pass this exam, and we really want to get you one step closer to getting your FSA.